Hi, good morning. This is going to be the fourth lecture in the series on topology, and I had already given, if I guess right, about 9 examples of topological spaces, and today we will give 2 more, and these about a dozen or so. That will be our mainstay throughout the course. Almost all concepts will illustrate with these examples, so learn them thoroughly, and you will also see how to think abstractly is enhanced by small questions which I keep asking about once I define the topology, right? Then I ask very small questions and try to learn that art. That will really help you. Okay, yeah, so this is the most important example, and example 10, right? So what I want to do, I am going to take x equal to r again, right? Now I am going to look at set of a class of subsets of the form a comma b, where a is less than b and they are in R, right? What kind of interval? Do you notice that it's closed at a, open at b, right? For example, 0 1, 0 is included, 1 is not included. Okay, that kind of thing, right? Now let's again recall how did I, so in the case of R with the usual topology, okay, when did I say U is open? The moment you give me A is in there, I wanted to say there is an R positive, so that A minus R to A plus R, this open interval is contained in U. Do you remember that? This is how we define the usual topology, and more generally we define any metric space XD. U is open. If you give me an A, there is an R positive, so that BR is contained in U. Keep that in mind. Okay, this will motivate how I am going to define here. So how am I going to define here? Okay, so if U is empty, nothing to worry. Suppose U is not empty, okay, then for every X here, I want, okay, for every X in U, there is a B which may depend upon X, thus that this interval is contained in U. Do you understand this? This is my definition of an open set. Okay, so I am going to define tau L. This is called lower limit topology, on R, right? So quickly recall, how do I define? So the tau L consists of all U subset of R, so that for every X in U there exists a real number B, so that X B is contained in U. So you have just have to focus that attention, that's it. Yeah, now we will show that this is a topology, and this topology is called lower limit topology. And does empty set belong to that? Of course, because for every X in U, and if U is empty, you cannot find, right? If this is false, you understand that this is a negation, so empty set belong to this. Because if you say empty set does not belong to this, what does that mean? There exists some X in empty set, so that this condition is fail. But the moment you say there exists some X, that's already a contradiction. Do you understand? Therefore, this is correct. Learn this kind of logic thoroughly. If necessary, go back to my foundation video, you will learn this kinds of stuff. Okay, right? Okay, therefore, does R belong to this? Of course, right? Give me any X, then X to take anything like X plus 1, that's going to be an R, right? Sorry, I wrote the wrong thing. X to X plus 1. This is wrong. This is contained in R, right? Therefore, this also is true, right? Okay. Next, okay, suppose UI is a collection and tau L, then I want to know whether union UI is in tau L. Okay, let X belong to that. When X belong to that, what does that mean? There is a J, so that X belong to UJ. And what do I know about UJ? UJ belong to tau L. That means there exists a B, so that X B is contained in UJ, and hence is contained in union UI. Is that clear to all? So second condition is also done. Third is, suppose U belong to towel and V belong to towel. Okay, if U intersection V is empty, nothing to prove. So let's assume X belong to U intersection V. Right? Therefore, what do I know? Since X belong to U and U is in towel, there is a B1, such that X B1, this is contained in U, and similarly there is a B2, X B2 is contained in V. I am sure all of you know what to do now, right? Is there anybody who is struggling? Yeah? So this is my R and this is my X. Okay, and this is my B1 and this may be my B2. Okay, B. Right? Then I know. Or this may be my B1 or this may be my B2. Maybe this is my B, maybe this is my B2, this is my B1. So the answer is clear. Therefore, let B equal to minimum of B1, B2, then the set XB is in U intersection V. Do all of you agree with that? So what have we shown? We have shown that this is a topology. Topology is therefore a topology on X. On R. It's called the lower limit topology. As I said earlier, we have proved it is a topology, and don't stop. We should learn to play with it. Right? Let's look at the motivation thing. When I tried to show how I define open set, I used the analogy. Right? For example, if XD is a metric space, if U is open, then for any X in U, there is an R positive, so that BXR is contained in U. Right? And do you remember what was the more or less the first question your teacher asked or the book deals with? We have defined open set. Now we want to know whether open ball is an open set. Yes? Do you understand? So what kind of question should I ask here now? How many of you can guess? The question is, suppose look at this interval of the form AB. Does it belong to towel? Do you understand this question? Is it not interesting? Is something similar to, right? We define open balls to build open sets, right? Now we build these semi-open intervals to build open sets for the lower limit topology. So natural question is whether these building blocks themselves are open sets in the topology, new topology. Okay? You should get excited with this kind of questions. Okay, that's very obvious. Why? Okay, start with any X in AB, right? This is my A, this is my B, and start with any X. So X may even be this, right? If X equal to A, what do you think I will take? I will take AB itself, right? This is contained in AB. This is my U. Okay, I want to know this is open, right? Right? Now suppose I have an X such that A is less than X less than B. What do you think I will do? So this is my X. Then what will I do? I will take XB. Therefore, in any case, whether A is less than or equal to X less than B, okay, this is contained in AB. Right? Therefore, what did we understand? Therefore, we have seen for every AB, the semi-closed interval, this is an open set. Okay? Pause, review, proceed. Next question. Take an open interval AB. Yeah? I know this belongs to the usual topology. What is the question I want to ask now? Does it belong to tau L, the lower limit topology? Yeah? Again, let's look at thing A, B. Suppose I have an X, therefore A is less than X less than B. Okay? I am sure all of you can guess. Suppose this is my X. What do you think you will take? Obvious, right? Yes. What will you take? Take xb itself. This is contained in AB. This is your U. I want to know this is open, right? You start with any x here, right? Then I have to say whether there exists an element of this script B. Any script B is of the form semi-closed interval. Have I got it? Yeah. Therefore, what is the claim? What is the conclusion? Therefore, AB belongs to tau L. Yeah. Okay. If I had understood this, then there is yet another natural question I would like to ask. Can somebody think of it? I know any open interval which is open in the usual topology is open in the lower limit topology. Alright? Now suppose, what is the next question I can ask? If you give me any open set U in tau U, that is, which is open in the usual topology, I know that, okay, U is of the form, okay, x minus Rx, x plus Rx, as x is in U, right? For each x in U, there is an R such that x minus R to x plus R, that interval is contained in U, right? Therefore, U is the union of this. Do you understand this? Okay, please check. Remember, this is why I asked you to review arbitrary union and intersection of family of subsets, so that you should be comfortable. Okay, you should don't take it for granted. Okay, so this I have to check. I hope you had understood, but check it again. Right. Now what do I know? Each of this interval x minus Rx, x plus Rx, okay, call it j of x, right? This is the interval. Thus belong to tau L. That's just now we proved, right? Any open interval is open in the lower limit topology. Therefore this is open. Now what is U? U is a union of open sets in the lower limit topology. Therefore U itself belong to tau L. Do you understand that? Yeah? Make sure that you understand. So what is the relation between the usual topology and the lower limit topology? Anything which is open in the usual topology is open in the lower limit topology. That means any element here tau U is contained in belongs to tau L. Therefore this is the key. Therefore this is the conclusion. So we have two topologies in R, namely usual topology and lower limit topology. What you have found is the usual topology is a subclass. Okay, it's a subset of the lower limit topology. One usually says that tau U is coarser than tau L, or tau L is finer than tau U. Okay, these are all jargon. Okay, so what have you found is this something. All right. Okay. Have you understood? Sure. Okay. Now let me look at a typical interval A comma B. We know it's in tau L, right? Yeah. Right. Let me ask, what is the complement? Call it as U. This is open. What is U complement? U complement. This is my A, B. Therefore, U complement is going to be minus infinity to A union closed at B to infinity. Yeah. Right. Now, what do I know about minus infinity to A? This is an open set in the usual topology. That implies that is already in the lower limit topology. Is that clear? Now let's look at B infinity. This certainly is not in usual open in the usual topology, but give me any x in B infinity, right? Then x to x plus 1, this will be contained in B infinity. Therefore, what does it say? It says that this infinite interval is it is not open in the usual topology, but it is open in the lower limit topology. Therefore, the complement of this is already open. Okay, its complement is minus infinity to A union B to infinity and this is open interval, this is also an element of towel, therefore this union is in towel, that is open. You see that? Yeah, okay. So there are few more questions I can ask, but I think that's enough. Okay, this already given a taste of what we want to do. So let me move on to the next example 11. And as I said, this will be essentially the last example. Okay, unlike the earlier case, what I will do is now I will work with an abstract thing itself. Let X be any non-empty set. Okay, let A be a partition of X. That means script A is a collection AI, I in I. So that what do I know? X is union AI, and what do I know about AI and AJ pi is not equal to J? Empty. You understand that? You usually write this as X equal to sometime like this, A or some such thing. Okay, it only says X is a disjoint union of pairwise disjoint union of AIs. Do you understand this? Right? Okay. Now I want to define a topology using a partition. Okay, so tau script A. Okay, this is U, where U is a union of a subfamily of A. Okay, so what does this mean? This means that if you give me a set U, a subset of X, when does U belong to tau of A? You should understand this. Okay, that means this means there exists a subset J of I, the indexing set, right? And such that my U is union of AI, I running over only J. Have you understood? To make sure that you understand properly, let me look at a simple example. Suppose my script A consists of only finitely many things, A1 to AN. Well, let us say even A 100. Right? Now what are all the possible subsets? Now you understand, right? Take any subset, okay, J of 1 to 100. For example, my J could be all odd integers, right? Then I can define A of J. What is A of J? The union of AI, where I runs over J. That is A1 union A3, etc. union A99. That's it. Do you follow that? Are you sure? Yeah? Okay. So please understand this. Pause, review, proceed. So when does U belong to A? This. So in particular, I am allowing empty sync also. Okay, because if J is empty, that union will be empty set. And if J equal to all of I, that will be all of X. I will come to that. Do you understand this? Pause, review, proceed. I want you to understand when does U belong to this. This is the crucial thing. If you want to master this, you should learn this very well. Yeah. So as I said, if I take J equal to empty set, then union I in J, okay, this is empty set, therefore it belongs to tau A. And similarly, if I take J equal to all of I, then remember it's a partition, therefore I over J is X, therefore that also belongs to tau of A. You follow that? Yeah. So the first condition is met. What is the second condition? Second condition is, let me say, now since I had already used I should think of some other notation. So let me say U alpha in some lambda. This is a collection of tau A. This is a collection of elements of tau of A. I want to know whether union U alpha is in lambda, whether this belongs to tau of A. Right? Yeah. Now, what do I have to prove? Okay. there are various ways of doing. I'll first try to give a slightly intimidating method. Suppose U alpha belong to that. That means there is a J alpha, which is a subset of I. So that U alpha is union of I running over J alpha. Do you understand this? Make sure you understand. Because U alpha, depending upon this U, there is a J. Since U depends on alpha, J depends on alpha, which is a subset of I. Then U, what should be U alpha according to our definition? You should be union of A, where I runs only over J alpha, right? Therefore, what will be union of U alpha? Alpha is in lambda. This will be alpha is in lambda, and union of I in J alpha of AI, right? Have you understood? Yeah, right. So what have we shown now? We have shown that this is again a union of elements coming from A, except I may not have written what is the family, but that's very clear. Do you understand? Okay. This is why you have to learn arbitrary union and intersection of families of sets. Please visit my videos again. Okay, right. So there is another method. Suppose I say U belong to tau of A. Okay. Do you think this is clear? If and only for every x in U, okay, there exists a I in script A, so that Ax belong to a I and A is contained in U. Do you accept it? Yeah, please check. Okay. Because if that be the case, if you want to say this A may be A of x, therefore again my U is going to be x in U of, okay, A. That's it. So it's a union of subset of this. Yeah, okay. So maybe let me define tau of A with this method then. This set of all U in U subset of x, so that for all x in U there exists A in script A, so that x belongs to A and A is contained in U. Okay. Then as proceeding as earlier, tau A is a topology on X called partition topology, associated to the partition. Okay, if you change the partition, the topology may also change, right? Okay, let us look at some easy observations. Suppose your X, my partition consists of all singletons, right? All singletons, right? Now what is the topology? How many of you can guess? It's a discrete topology. Because what does it say? It says that if I take any set U subset of U, then it's open. Why? U is union of singleton X, X varies over U, therefore this belongs to tau of A. Therefore every subset of X is in tau of A. That means tau of A is the power set. Therefore it's a discrete topology. What should be the next question I should ask? Now my partition consists of only X singleton, right? What do you think the topology is? I'm sure all of you know. And discrete topology. Tau of A is discrete. Okay, please check. These are all easy. I had already done a lot of such examples, so you should know. Now we come to special case, so that I can ask lot of questions. Okay, what is the special case? Let me take x equal to n. What is the partition? Partition is, okay, this one, collection of all 2n minus 1 2n, that is as n varies over natural numbers. What does that mean? So if a belongs to this, what does it mean? A is of the form 2n minus 1 2n. So you can think of an equal to 2n minus 1 2n. That is it. So these are all the things, right? So what you follow, therefore this will be 1 2 and 3 4 and okay 9 10 and so on. These are the only things. Do you understand this? Okay, so I want to understand the partition topology topic. I want to, and the idea is to understand now in this special case. Let us go one by one. Suppose I say U is open. Okay, let me ask this question. Suppose I give 5, okay, a natural number. What is the simplest open set that contains 5? You know the answer, right? If 5 belong to U, okay, suppose U is such an open set. If 5 belong to U, okay, then what do I know? 5 6 also should belong to U. You understand that? Therefore 5 6 is the simplest open set. All of you agree with that? Please pay attention. Yeah. And suppose I say 10 belong to n. What do I know? 10 is 2 times 5. Therefore I know 9 must also belong to U. Then 9 also belong to U. Therefore the simplest open set should be 9 and 10. More generally, okay, if n is given and I am looking for the simplest open set U, right, then U must be, can you guess? It should be n and n plus 1 if n is odd, and if it will be n and n minus 1, or should I write n minus 1? N minus 1 comma n if n is even. You understand that? These are the simplest open sets, right? Therefore I can characterize U. So when does U belong to tau of A? U belong to tau of A if and only if for every n in U, okay, n plus 1 is contained in U if n is or and this and, you understand that? The whole thing must be true, and n minus 1 n is contained in U if n is even. Are you following? So suppose I take A equal to set of even integers in n. Is this open? No, because whenever an even integer is there, it's a predecessor, odd integer should be there, right? Similarly, if I take odd, whenever n is there, if it is odd, then it's a successor, namely n plus 1, n is that even integer, next even integer must be there. That's not true. You follow that? Therefore these are all not open. Now let me ask the last question. Suppose my P is a set of primes in n. So what is the smallest topology? Okay, smallest open set U that contains P? That's a question. It's a very easy question if you think carefully. See, this is why I like taking concrete examples. because once I take, if I simply say X is a set, there is nothing I can do with that. Whereas the moment you say numbers, some such concrete thing, then there are a lot of things. I can think of some special elements like primes. Now given prime, there is something very interesting. Just now look at it. What did we talk about? Some set being open, not open, dependent upon, if you give me an n which is odd, then n and n plus 1 must be there. If you give me an n which is even in that set, then n minus 1 and n, the predecessor, and n should be there, if in the case of n even. Do you understand? So that clearly showed, if I want an open set U which contains P, then what should I worry about? This is how you learn to solve problems. I have to worry about the prime being odd or even. Do you understand that? Therefore, okay, so if P is an odd prime, okay, then P and P plus 1 must be contained in U, right? And P is an even prime. In that case, there is only one prime, even prime. What is that? That is P equal to 2. Therefore 1 and 2 should be in U. You follow that? Okay. Now therefore what is the smallest open set containing all primes? Is U, where U equal to 1 and 2 union P odd prime P and P plus 1. Is this open? Because these are all open sets, union of open sets, and it's a topology, therefore this union is open, and this is it. Okay, this is an open set. And why it's the smallest? Because whenever U is open, if P and odd prime belong to that, I know P and P plus 1 must be there. And similarly, if P is 2, it's an even, therefore 1 and 2 must be there. You follow that? Therefore this is the smallest. Okay, pause, review, proceed. I hope you all enjoyed these 4 lectures, and as a sequel, okay, you can look at a topological proof of the infinity of primes. Okay, this video also talks about one interesting topology on set of integers, and from that topology we conclude the set of primes is infinite. You like it, and if you have gone through all these 4 videos, you will find that also very much easier. Okay, please go through all these 5 at least once or twice, discuss these things with your friends. Okay, go through all these 4 lectures and also the 5th lecture, infinity of primes, and you will enjoy. Okay, you would have learned how to think abstractly in topology. Many students' problem is this. Okay, but notice that after these things, when we are going to things, we are going to be more geometric also. So it's a beautiful combination of abstraction and geometric ideas. You will love it. Okay, take care, stay safe, we will meet again.